So we did talk about gas laws last year in general chemistry, so this is going to be just a quick refresher. Gas laws all deal with the relationship, so if we were to change the pressure, what happens to the volume? If we change the temperature, what happens to the pressure? All of those kind of things. And then, of course, the ideal gas law that lets us analyze a particular gas. So the first one is Boyle's law. Boyle's law is the relationship between pressure and volume, and it's P1 times V1 equals P2 times V2. What that means is the initial pressure times the initial volume will be equal to the final volume times the final pressure. And then what this shows us, since it's a multiplication, is that volume is inversely proportional to pressure. So if volume goes up, pressure goes down. If pressure goes down, volume goes up. We can imagine a scenario like this when we've got a larger volume. The pressure then of that gas is going to be less than it would be if we were to push this down. So we've got half the volume. It's going to require twice the pressure then to hold that down. If there's a smaller area like this, that means the gas particles are going to be hitting the sides more often. They have less space to roam. If they hit the sides more often, what does side hitting cause? Yeah, it causes pressure. And of course, there's Charles' law, V1 over T1 equals V2 over T2. Something important with this and all temperature problems with gases, you must use Kelvin. You have to use absolute temperature. Otherwise, Celsius can go negative, and if you use a negative in an equation like this, you'll wind up with a negative volume, and that can't exist. What this one does show us, though, is that volume is directly proportional to temperature. So if volume goes up, temperature goes up. If temperature goes down, volume goes down. So here's kind of the same situation where we cut the volume in half on a gas. So in this one, they've got a lot more space to move around, and so they're just going to be bouncing a little bit lollygagging in there. But in this side, when they're going to be bouncing off those walls more often, that means bam, 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 bam. More collisions. If there's more collisions, that's going to create more kinetic energy. More kinetic energy, hey, more temperature. And then finally, the combined gas law. So this relates everything. It keeps pressure and volume as inversely proportional, and volume and pressure and temperature as directly proportional. Once again, temperature has to be in Kelvin. Let's do a quick practice problem with the combined gas law. So a cylinder of gas is kept at a constant volume as the temperature increases from 24.1 to 326.4 degrees Celsius. If the initial pressure is 1.01 atmospheres, what is the final pressure in millimeters of mercury? Okay, so we're going to use the combined gas law here. And we notice in this that the constant volume, okay, so that means it's a steel cylinder or something like that that can't swell or expand, so the volume is going to stay the same. If the volume stays the same, that means on our combined gas law, we can leave that out. It's going to cancel each other out anyway. And so the equation that we're left with is P1 over T1 equals P2 over T2. So now we can take some values and plug those in there. The initial pressure is 1.01 atmospheres, and so that would be our P1. And then the temperature goes from 24.1 to 326.4. We can convert that to Kelvin, and that would be T1 and T2 respectively. We need to find P2 because that's the final pressure. So then here's our setup with our numbers plugged in. In order to get from Celsius to Kelvin, we're going to add 273 to both of those temperatures. We can now solve for P2, and we can do that by cross-multiplying, and when that happens, we should get 2.04 atmospheres. Now, this makes sense. The pressure went up, and the pressure went up because the temperature went up. We know that pressure and temperature are directly proportional, so since temperature goes up, pressure goes up as well. In fact, if we look at our Kelvin temperatures, this is roughly 300 Kelvin, and this is about 600 Kelvin, and so the temperature doubled, and hey, look at that, so did the pressure. This question wants our pressure in millimeters of mercury, so we're going to need to convert that over. So if we have 2.04 atmospheres, the conversion from atmospheres into millimeters of mercury, or torr, there is 760 millimeters of mercury for every 1 atmosphere. And so then atmospheres cancel out atmospheres. We can solve this and get 1.55 times 10 to the third millimeters of mercury. Okay, a new gas principle to AP chemistry is Avogadro's principle. And this, as you expected, deals with Avogadro's number, or the number of particles inside of a gas. So equal volumes of different gases at the exact same temperature and pressure will contain an equal number of particles regardless of the molecules. So if we have 4 balloons here, all of them that have 1.5 liter capacity, and they contain different gases, helium, argon, nitrogen, and oxygen. They will have the exact same number of particles. There's a calculation we can do, and in each of these cases, they contain 6.7 times 10 to the negative second moles of gaseous particles. It doesn't matter that helium molecules are tiny and oxygen and nitrogen molecules are going to be larger. They're all going to have the exact same number of particles. So remember that all gases of equal volumes, equal temperature, equal pressure will have the same number of particles. Something else that's unique to gases is STP. STP is a standard state of conditions that scientists have agreed. This is where gases behave most ideally. So if we're going to research gases, we want them under these conditions. And the conditions are 0 degrees Celsius and 1 atmosphere. So that would be 273 Kelvin, 1 atmosphere of pressure. Keep in mind, this is different than the standard states in thermochemistry. In thermochemistry, it was 25 degrees Celsius and 1 atmosphere. STP for gases, though, is 0 degrees Celsius. So remember Avogadro's principle that we talked about a couple slides ago? The one that said that equal volumes of different gases, same temperature, same pressure, will have the same number of particles? Here it is at STP. So at STP, 1 mole of gas, so that's 6.022 times 10 to the 23rd particles, will occupy exactly 22.4 liters of space. So if we have a 22.4 liter container, and it's at 0 degrees Celsius, 1 atmosphere, there will be exactly 1 mole of gaseous particles inside of that container. It does not matter what the gas is. So for example, the room I'm in is about 12 meters by 17 meters by 2.8 meters, which then would have a volume of 571,200 liters. So if we want to figure out how many individual gas molecules there's floating around in here, I don't have to figure out what the different kinds of gas are inside this room. It doesn't matter, Avogadro's principle. So if we've got 571,200 liters, there is 22.4 liters for every 1 mole, since we are at STP. And 1 mole is how many particles? Yeah, it's Avogadro's number, 6.022 times 10 to the 23rd molecules. And that comes out to be 1.54 times 10 to the 28th molecules. So inside this room, there would be that many gas molecules floating around. Now comes the ideal gas equation. So the ideal gas equation is one that we use to analyze a particular sample. The other ones, Boyle's gas law or Charles, and then the combined gas law, all of those use a changing system. So if we change pressure, temperature, or volume, ideal gas equation problems we're going to recognize because we have a particular gas under a particular state of conditions, nothing's changing, and we're trying to figure something out about it. Temperature, of course, still has to be in Kelvin. Pressure now has to be in atmospheres. Volume has to be in liters. And the reason for that is this little guy right here, which is R, which stands for ratio. So it's the ratio of liters times atmospheres divided by temperature times moles. And since we have liters, atmospheres, kelvins, and moles, we have to have liters, atmospheres, kelvins, and moles in our equation. And we use the Pervnert equation to get any one of these 4 conditions. So if we need to figure out temperature, we would use Pervnert. If we need to figure out volume, we use Pervnert, as long as nothing is changing. So here's an example. We have an 8.5 liter tank that contains helium gas, 16.9 atmospheres, 25 degrees Celsius. How many moles of helium are available for making the balloons? How many moles of helium is there inside of that tank? Now you notice nothing here is changing. It doesn't say temperature is going from 25 to 100 or volume is going from 8.5 down to 3. Everything's the same, so that should be a signal to our little AP chemistry brains that this is a Pervnert question. So here's our equation. We, of course, know what R is already. Let's go through and identify the other pieces. So right here, 8.5 liters, that's volume. 16.9 atmospheres, that's pressure. And 25 degrees Celsius, that is temperature. And then the question is asking us how many moles is there, so that is in. So we do have pressure, volume, and temperature. We're looking for the number of moles. So I'm going to rearrange this equation and do it by dividing both sides by RT, which means that the number of moles is going to be equal to the pressure times the volume divided by R times the temperature. All right, and we can see here from this equation, atmospheres cancels out atmospheres, liters cancels out liters, Kelvin cancels out Kelvin. We are left with moles, and that's perfect because that's what we're trying to solve for. And so in this case, is going to equal 5.9. So that means there's going to be 5.9 moles of helium inside of that tank.